It's a wonderful turnout. And what I'd like to do is speak for about between 7 o'clock to 8 o'clock with a quick presentation. We would like to get about a half hour worth of questions too from you, so get ready for those. And believe me, if you don't have enough questions, I'll just keep on going. Just kidding. What I'd like to talk to you a little bit about tonight is, of course, the evidence for God from contemporary physics and especially contemporary cosmology. So we're going to spend the lion's share of time on it. But, just sort of looking around, the popular press today, a lot of, what I would call misnomers about the Catholic Church and about religion have kind of, been spread about, and I just thought I might just talk a little bit, just to start off with for a few seconds, about some of the figures, Catholic priests, as a matter of fact, Catholic clerics that have been involved in science from its inception. Just to give an idea, that, what's been said, maybe about Giordano Bruno. By the way, Giordano Bruno was not tried because of anything he said about science. He was a heretic on 4 other levels, quite genuinely. And so, for all intents and purposes, it had nothing to do with science. If you look up, at some of these folks here on the PowerPoints, you'll see Nicholas Copernicus. A lot of people have thought that the church persecuted Galileo because Galileo believed in the heliocentric universe. That wasn't the reason for it. The person who first devised and mathematically approved the possibility of a heliocentric universe was Nicholas Copernicus, as you probably know, and he was a Catholic cleric. He was even a canon lawyer within the Catholic Church who had this wonderful habit of mathematics and astronomy, and of course came up with the first version of the heliocentric universe. By the way, the Galileo controversy was not about the heliocentric universe or about science itself, as we'll see in a moment. Really, what it was about was, the Pope had asked Galileo to refrain from publishing his theory, his heliocentric theory, as a fact before there was enough evidence to actually show that. Now, about 200 years later, there was the evidence to actually show that heliocentrism was correct, and that was with a technique called stellar parallax. But up to that point, really there wasn't enough evidence. And what Galileo went ahead and did, and by the way, the Jesuits at the Roman College befriended Galileo. They thought he was tremendous. And in fact, the Jesuit mathematicians at the Roman College actually helped Galileo to prove his heliocentric theory. However, when he called the Pope a fool in his book, on the 2 new systems, the Jesuits kind of went, whoa, this is getting kind of radical here. And so they pulled back a little bit, and of course, he did publish it as a fact after he promised the Pope that he wouldn't, and the rest, as they say, is history. But it wasn't about the church being antithetical or against science. Had nothing to do with that at all. We can see a second figure here, also quite well known, Gregor Mendel. Pardon? Oh, I'm sorry. Gregor Mendel. And Gregor Mendel, as you know, was the father of contemporary quantitative genetics. He was not only an Augustinian monk, he was the abbot of his monastery, and so, of course, turned it into a half laboratory because he was abbot. We also have another figure up there, who is the head of contemporary stratigraphy and what's called modern geology, and of course fossils, and that's Nicholas Steno, who was not only a priest, he was a bishop, and he was a bishop in Denmark, a Catholic bishop in Denmark. The final figure you'll see is Father Georges Lemaitre. And Father Georges Lemaitre was a Belgian priest. He was a World War I hero, went off to study at MIT and also at Stanford, got his doctorate in physical cosmology, became a colleague of Einstein's. And Lemaitre is responsible for the most comprehensive cosmological theory and the most rigorously verified cosmological theory today, called the Big Bang Theory. And he discovered that in 1927. 3 years later, it was verified by Edwin Hubble, the very famous American astronomer there at Mount Wilson. And, well, again, the rest is history. But Georges Lemaitre called the theory at that time, the theory of the cosmic egg, and later on he called it the cosmic atom. It wasn't called the Big Bang Theory. That was named by Fred Hoyle, who was trying to cast aspersions upon it. He said, oh yes, that theory of, yes, what shall we call it? The Big Bang. And of course, that was supposed to be a snub, but of course, he later regretted that, as we shall see later on in the lecture, because it got so well proven. But in any case, no, the Catholic Church has not been against science. Many of its priests have been in the forefront of science. And of course, today, you still see Lemaitre Walker Spacetime, Lemaitre Constant, Lemaitre Possibilities, Lemaitre Matrices, etc., etc. So Georges Lemaitre, a good Belgian priest, is at the center of science. We have the Pontifical Academy of Sciences, and it's filled with Nobel Prize winners. The Jesuits, for sure, have an observatory down there in Tucson, Arizona, right next to the Kitt Peak Observatory, the University of Arizona. And of course, also we staff the observatory down in Chile. And of course, you can go to any of these websites, and there's the Catholic Church standing there at the forefront of science. So it's kind of regrettable that we're getting all this, I would say, very false press right now. And it's undeserved. But, I'll get off my bandwagon and get to the point. What can the church do, and or what can science do, and what can't science do, for starters? I had a debate with Stephen Hawking a while back on the Larry King Show, along with his colleague Leonard Mladenov and Deepak Chopra, that wonderful man. But throughout the debate, the matter of whether or not science could actually say whether the universe needed a creator, or could say definitively that science doesn't need a creator, that was part of the debate that came up, and we'll be talking about nothingness in a minute. The point, though, of all of this is just three brief principles that we have to establish from the beginning. Number one, science cannot disprove God. I don't care what anybody tells you. I don't care if they have a PhD. Science cannot disprove God. Why is that? Because scientific evidence must be based on observation. Measurements which are observable, data which is observable, comparative reflex and hypothetical deductive things which are essentially observable. Now here is the essential problem. God is outside the universe. All observational evidence is within the universe. You cannot use observational data from within the universe to disprove a God who is outside the universe, transcending the universe. It's absolutely impossible. You can't use data from within the cartoon to disprove the cartoonist. It's impossible. That's the first thing. Second thing, Stephen Hawking, during the debate, made that one contention. Well, we know today, we now have string theory, or now what's called M theory, 11-dimensional configurations of strings. But the key thing is, as we now know, he said, that the universe does not need a creator. No, we don't. We don't know anything of the kind. Why is that? Because science is not only based on observational evidence, science is an inductive discipline. It moves from particular observational data, and then it tries to put all that data together in theories. And once it gets a theory, a comprehensive theory, that'll explain all the particular data, scientists say we're going to accept this as a rigorously verified theory until what? Something else comes along that could disprove it. Exactly. Science, by its very nature, because it's inductive, because it moves from particulars to universals, to particulars to generals, because of that, science must always be open to a new datum which could literally lead to a scientific revolution. You know, a lot of physicists thought that the Newtonian physical system was absolutely correct. Just like Stephen Hawking believes that string theory is, by the way, there's not a scintilla of evidence yet for string theory, and my friends who are stringers are really getting worried out there. But the point I'm trying to get to is, for all intents and purposes, we can't possibly say that a physical theory disproves a creation for certain, because we simply have to remain open to new data at all times. There can be no way we could say our theory is complete. Scientists don't know what they don't know until they discover it. That's the point of inductive disciplines. It must be respected. So you might think to yourself, well, Spitzer, if that's true, if science can't disprove God, and science can't even show that the universe does not need a creator, how can you get off saying that there's physical evidence that the universe does need a creator? How can you say that? From one very simple problem, and that is what's called a beginning of time. Not necessarily a beginning of time in this universe, though that could be the only universe there is. Our universe might be it. And by the way, we have no idea whether there's a multiverse. More on multiverses in a moment. We have no idea whether there could be a string universe in the higher dimensional space of string theory or M theory. We don't know whether that exists or not. It's an interesting possibility. We don't know whether the universe has been, expanding and contracting and expanding and contracting. But we do know one thing from physical evidence, that all three of those configurations need a beginning. Our universe needs a beginning. Multiverses need a beginning. More on that in a moment. Oscillating universes or bouncing universes need a beginning. More on that in a moment. Higher dimensional space string universes need a beginning. More on that in a moment. Every one of them needs a beginning. And that's why we're at a very interesting juncture. And we'll talk about the evidence for that beginning in just a minute. But we're at an interesting juncture right now, where we're getting to the point where all known configurations of matter, of physics, physical energy and space-time, seem to need a beginning. Now, what is the exact, why is that so important that physical reality may well have a beginning? Because if there really is a beginning to physical reality, the beginning of physical reality is also the beginning of space-time. It's the beginning of space and time. It's even could be the beginning of the time of a multiverse. And if we have a beginning of time, then prior to that beginning, the universe and even physical space and time itself was nothing. And if the universe was nothing, then the only thing it could do was nothing. Because the only thing nothing can do is nothing. That's the real meaning of nothing. Now, if physical reality prior to the beginning was nothing and could only do nothing, then something else had to move physical reality from nothing to something, because it could not have moved itself from nothing to something, because it was nothing and could only do nothing. This is the problem. You might be wondering, why did Stephen Hawking write at the end of his book, The Grand Design, that nothing was the equations of gravity? Because he desperately wants nothing not to be nothing. Because if nothing's really nothing, then if physical reality has a beginning prior to which physical reality was nothing, then physical reality is going to need a creator. A creation event outside of physical reality itself. That's the consequences. And by the way, Larry King actually got this. I mean, at one point I actually said during the debate, honestly, you can't claim that nothing is the equations of gravity. I mean, if you claim this, then you're going to say either that nothing is something, or you're going to say that the equations of gravity are nothing. Neither of those statements works. And if there was equations of gravity prior to the existence of physical reality, what would equations of gravity without a physical universe be? Well, they'd have to be some kind of mentative, some kind of intellective reality, which begs the question, in whose mind? A mind outside of physical reality sounds like God to me. Stephen, as I said, Larry King actually said at one point, Leonard Mladenov was on the debate, and he goes, yeah, Leonard, how can you make something come from nothing? My point is, you can't. And if that's the case, then maybe physics is drawing very, very close to showing a creation event. Well, we better get to the evidence. That's the consequence. In fact, Stephen Barr, one of my very good colleagues who's on a board of directors of the Magis Center, actually wrote an article for First Things called Much Ado About Nothing. And the reason, of course, is pretty clear. Okay, let's get down to the evidence. You'll see in this triangle three different areas there: space-time geometry proofs, entropy, and fine-tuning or anthropic coincidences. We're going to take each one of these very, very briefly, but what I want you to do tonight is to, if you could, just scribble down our website. If you want the actual mathematical proofs that I'll be talking about, you can just go to magiscenter.com. Just go to our first landing page called Faith and Science, and all of it is there free of charge. Free 2-hour video by yours truly, free workbook, free lectures by Alexander Vilenkin. We'll talk about him in a moment on the mathematics of a beginning and so forth. You can get it. It's all there. Magiscenter.com, free of charge. Just go to the first landing page, Faith and Science, Faith and Reason, and you'll see it. But let's get down to these three evidentiary points. The first two, going across the top of the triangle there, space-time geometry proofs and entropy, are going to point to a beginning, not just of our universe, but a beginning of physical reality. The third, namely fine-tuning and anthropic coincidences, is actually going to point to the intelligence of the Creator itself. So let's just go through this really quickly. But why get into space-time geometry proofs and so forth? Because this universe might not be all there is. Now, we do know a lot about this universe. There's a lot of reasons for thinking that the Big Bang is true. A lot of reasons. Basically about 24 different independent verifications of it. It comes originally from Edwin Hubble's survey of the heavens, And that, of course, is complemented by Penzias and Wilson, who later discovered the 2.7 degree Kelvin uniformly distributed radiation, which showed, that this radiation had to emerge in basically a cosmic event. It had to emerge at a time when the universe was almost homogeneous in order for it to be spread evenly throughout the entire universe. Later on, of course, it was verified by the two COBE satellites, the Cosmic Background Explorer satellites 1 and 2, the Wilkinson Microwave Anisotropy Probe, and then finally the Planck satellite. And so we've got a lot of different ways of verifying the Big Bang. What do we think about the universe today? Our universe, the one we can have observational data about. What do we think of it? We think it's 13.8 billion years old. So 13.8 billion years old, plus or minus 100 million years. There's a lot of very good evidence for that age of the universe. We also think that the universe is somewhere in the neighborhood of about 100 billion light years in radius, something along those lines. We also think that the universe has approximately 10 to the 80th baryons worth of visible matter. And visible matter is the kind that make all the forces of the universe work, right? So this is where you're going to have electromagnetic forces, strong nuclear force, the weak force. This is where you have matter that actually absorbs and emits light, absorbs and emits energy. So we've got about 5% of our universe is visible matter, and there's about 10 to the 80th baryons worth. A baryon is a heavy particle like a proton or a neutron. 10 to the 80th is a lot, but it's very finite. Very, very finite. And furthermore, we probably have about 30% of our universe is dark matter. Dark matter doesn't absorb or emit light or energy in the way that visible matter does. So we've got about 6 times more dark matter than we do visible matter. And 70% of our universe is what's called dark energy. And dark energy is not like matter at all. So visible matter and dark matter are one end of the spectrum, and dark energy is at the other end of the spectrum. And think of dark energy as kind of like a field that attaches itself to the space-time field, and it causes our universe to expand at an accelerated rate. So dark energy is making our universe expand at an accelerated rate right now. 70% of our universe is dark energy. Because the cosmological constant is positive, the universe is not going to collapse in upon itself. It's going to keep expanding, and it will continue to expand until it finally burns out. Well, first all the stars in the universe will burn out, and then eventually the universe will reach thermodynamic equilibrium, a heat death, where absolutely no work will be possible from within the universe. That's what's very likely to happen. You can't have 70% dark energy. Dark energy then interacts with the space-time field in exactly the opposite way of matter. Matter causes an increased curvature of space-time, and that's going to cause what looks like an attraction effect, and dark energy is going to cause a repulsion of space-time, right? It's like the mirror image, if I can put it that way, of matter. So it's going to cause the space-time field to accelerate. That's basically kind of what we know about our universe, the age of our universe. It might be the totality of physical reality. There's not one scintilla of physical evidence that would say that the Big Bang isn't the beginning of physical reality as well as the beginning of the universe. There's not one scintilla of evidence, physical evidence, that would say there's a multiverse or a higher dimensional space universe, etc. But we have to keep those possibilities in mind because they are possible. We've got this Planck era of the universe, quantum gravity, which causes some possibilities. We also have what's called an inflationary condition that's produced by dark energy, and that inflationary condition causes the possibility of a multiverse. causes, and you put the two together, and you can actually have higher dimensional universes in the higher dimensional space of string theory, where you have like 2 3-dimensional membranes colliding in a 4-dimensional bulk space-time, burping out additional universes, etc. So you have some fascinating possibilities that maybe physical reality goes beyond this universe. What's a multiverse? A multiverse is like it's a mega universe, right? And in this mega universe, right, little bubble universes are popping out. And there's a reason why they're popping out. You can ask this in the Q&A. It's a very good reason for it that's produced by an inflationary condition. Essentially, though, our universe, according to this hypothesis, would be one bubble universe amidst trillions upon trillions of other bubble universes that are being coughed out in the multiverse. That's a possibility. That would mean the universe is, that physical reality is much bigger than we think it is, and would mean that it goes back further in time than we think it does, than our universe does. However, what does that mean? It means nothing, because as we'll see in a moment, all multiverses must have a beginning. You cannot have a multiverse without a beginning. The same thing holds true. There might actually be a bouncing effect. Now, a lot of physicists think there's not a bouncing effect, because if you have 70% dark energy in our universe as we know it today, which means the universe is going to keep accelerating and it's going to keep expanding forever, right? If that's the case, then for all intents and purposes, I can assure you of this: there's going to be no way that you're going to have a collapse of that universe. So how could you have a collapse of the universe in a previous stage before this one? You'd have to get rid of the dark energy, and then you'd have to pop it back in at some point. Most physicists do not think that this is physically realistic. So for all intents and purposes, there's only one expansion, and there's only going to be one expansion, and that's that. There probably weren't bounces in the past. However, we ought to consider the possibility. Maybe the dark energy disappeared in the past and reappeared right afterwards. Possibly. So let's entertain it. It still needs a beginning. And the same thing with higher dimensional space universes and so forth. Why can we be so confident about this? Well, it goes actually back to Stephen Hawking himself. Stephen Hawking and Roger Penrose created the first singularity theorems back in the the late 60s, and that was called the Hawking-Penrose singularity. But of course, that singularity theorem changed, and the reason that it changed was because we discovered quantum gravity and inflation from dark energy. So those two things changed the whole scale of the Big Bang, and you kind of have to redo your theory from that point on. What I'm trying to say, though, is a multiverse is possible, but so we had to redo these theories, and it starts in 1993. What's a space-time geometry theory? Essentially, the configuration of space-time geometry enables you to make predictions. Not only predictions about our universe, but predictions about other possible universes. Predictions about even multiverses. So you can actually say, if space-time geometry is this way, then you'd have to have a beginning. If it's that other way, then you wouldn't have to have a beginning, and so forth and so on. In 1993, two individuals, Dr. Alexander Vilenkin, who's the director of the Institute of Cosmology at Tufts University in Boston, came together with Dr. Arvind Borda, who was just up the street at the University of California, Santa Barbara, at the Kavli Institute there. The two of them came together and created what's called the first space-time geometry proof that accounted for inflationary theory and quantum gravity. Essentially, that proof had 4 conditions. And by the way, if you want to know the 4 conditions, where would you go? magiscenter.com, and to the first landing page, and there you will find out intimate detail, all the conditions you'd need to know. But anyway, this had 4 conditions. And in 1993, it was thought that our universe and other inflationary universes met all 4 of those conditions. And in meeting all 4 of those conditions, then our universe, other inflationary universes, would have to have a beginning. In 1997, though, they discovered a very small loophole. Just a little possibility that you could get out of this proof in what was called the high energy condition of their space-time geometry proof, the third condition of their space-time geometry proof. And once that was done, what wound up happening is people thought, okay, this proof is not completely airtight. There's a small loophole in it. But then Dr. Alan Guth came along, who had the high chair of cosmology at MIT, and he also is the father of inflationary theory. Guth came along and actually said in 1999, well, to be very honest with you, this condition, this loophole is so remote as to be unimportant. Then he went ahead and modeled all the known inflationary model universes we could get, and this was what he basically came up with after the modeling in 1999. He said all known possible inflationary universes and models of inflationary universes can be eternal into the future, but they cannot be eternal into the past. Every single one of them must have a beginning. Whoa, this is immense, immense. But of course, it didn't rule out completely a multiverse. It sort of ruled out, ruled out a beginning of a multiverse. But the key thing to remember is that even though this proof it still has a loophole in it, it still is a very valid and usable proof today. But in 2003, all 3 of these physicists came together. Guth from MIT, Vilenkin from Tufts, and Bede from Santa Barbara all came together. And they created what is now referred to today as the BVG proof, the Bede-Vilenkin-Guth proof, and or the Bede-Vilenkin-Guth theorem, same thing, right? Theorem is not a theory, a theorem is a proof, right? And so the Bede-Vilenkin-Guth proof of 2003 has but one condition, ladies and gentlemen, only one condition for a beginning of a physical configuration. And that is that the average Hubble expansion be greater than 0. That's it. What's a Hubble expansion? A Hubble expansion is the expansion rate of a universe as a whole. So if the expansion rate of a universe or multiverse as a whole is greater than 0, no matter how small, if it's greater than 0, that configuration needs a beginning. Now, this is a very easy 6-step proof. And if you want to know it, we can actually go through it in the Q&A period. But for the time being, you're going to have to take my word for it. Or you could go to magiscenter.com, and you could see the entire proof explained, and you could also see the mathematical proof. There's a logical proof, and there's a mathematical proof, and both proofs are there on the website. By the way, it's a very good proof. It's a very difficult proof to overcome for 2 reasons. Number one, there's only one condition. When you have 4 conditions, you can start finding loopholes as you assemble the condition. But if you only have one condition, it's really, really hard to disprove. And the second thing is, this one condition is absolutely universally applicable. Why so? Well, let's take a look at our universe. Our universe has dark energy. It's inflationary. all other bubble universes in a hypothetical multiverse would also have to have a birth point which was smaller than, of course, the total diameter of the universe that they would have today, which means, of course, they too would have to be expanding. If they're expanding, they have an average Hubble expansion greater than 0. But moreover, every multiverse, you cannot have a multiverse that is not inflationary. The only thing that makes a multiverse possible is inflation. But wait a minute, if a multiverse has to be inflationary, it must have an average Hubble expansion greater than 0. But if it has an average Hubble expansion greater than 0, it must have a beginning. What about higher dimensional space universes? Those 2 3-dimensional membranes that are colliding in the 4-dimensional bulk space-time, burping out additional universes. Every one of those conditions has to have nucleation, which means that it is expanding. It has an average Hubble expansion greater than 0. It is very difficult to get out of this. Oh, by the way, a bouncing universe that expands and contracts, if it begins with an expansion, which it would have to in any known scenario, the average Hubble expansion would have to be greater than 0, which means it must have a beginning. Very difficult to get out of this proof. Now, there is one possible way of trying to escape a beginning from the Borde-Vilenkin and Guth proof. But if you're going to escape a beginning from the proof by the Borde-Vilenkin and Guth proof, what are you going to have to do? You got to make sure that this configuration doesn't have an average Hubble expansion greater than 0. So you've got to make sure then that universe is not expanding. Well, how do you do that? I've got it. A perfectly static universe. So, perhaps the universe, according to the conjecture of the eternally static universe, perhaps the universe was extending back, has been going on for an infinite amount of time. You with me? And its infinite amount of time is a static universe. And finally, one day, 13.8 billion years ago, it went boom. What's wrong with that postulate? Well, aside from the fact that, as Vilenkin and his colleague have already shown, it's quantum mechanically unstable, and that's going to disprove it right away. It's also a logical contradiction, ladies and gentlemen. Why is that? Because if you're going to have a condition that lasts for an infinite amount of time, it's got to be perfectly stable. You can't have a metastable or a partially unstable condition that's going to remain the same over an infinite amount of time. It's impossible. Therefore, you have to have a perfectly stable condition. Everybody with me so far? Now, when you get to the Big Bang 13.8 billion years ago, and we know that a Big Bang happened 13.8 billion years ago, the universe can't be perfectly stable anymore. There has to be some metastable element in it, because if there weren't some metastable element, some partially unstable element in it, it would have never unraveled and exploded. But wait a minute. In order for it to last an infinite amount of time, it has to be perfectly stable. And then in order for it to explode at the time of the Big Bang, it has to be partially unstable. That's a contradiction. A partially unstable, perfectly stable configuration. That's not good. John is 6'4" and 6'3" in the same respect at the same place and time. You can't say that. Anyway, it's quantum unstable. What's the point? There doesn't exist any known configuration today that doesn't require a beginning. We're at a point where it seems like all known physical configurations require a beginning. Now, I want to just take the entropy evidence very quickly and then get to a couple of statements from Alexander Vilenkin that might sum this up. But entropy is also very interesting because entropy, as Albert Einstein once observed, if every other physical law is modified, entropy, the second law of thermodynamics, is the one physical law that is unlikely to be modified because it is not based solely on a physical, chemical, or thermodynamic property. It's mathematical. Entropy draws its truth from probability theory. All ordered configurations are less probable than disordered ones. Well, what does that mean? I'm going to make this simple. Please don't hold me to it in the Q&A if I need to get more complex. But here's the basic thought. If you're looking at thermodynamics, disequilibrium is good in a physical system. Because if you have disequilibrium, then you've got some potential to do work. What's bad in a physical system is equilibrium. Because if a physical system is at perfect equilibrium, it is not going to be able to do any work. So we like disequilibrium of temperature. We like hot stars and cold space. That's good, disequilibrium. There's going to be some work coming out of that. We like disequilibrium of particle distribution, disequilibrium of pressure. All disequilibriums are great, and we call disequilibrium order. And that's a wonderful thing. But disequilibrium is very, very improbable. Equilibrium is always more probable. Every system is tending toward equilibrium. Eventually, all the hot places and cold places are going to even out to a warm place of equal temperature. Eventually, all those particle disequilibriums, a particle distribution disequilibrium, they're going to eventually find their way back to equilibrium. Eventually, all the pressure disequilibrium, they're going to find their way back to equilibrium. So here, just think about it this way for just 2 seconds. Every physical system needs some disequilibrium, some order in order to do physical work. But every time a physical system does some work, it uses up a little bit of its disequilibrium and never comes back with the same amount of disequilibrium that it had before. It loses a little bit of its order, and in losing a little bit of its order, it loses a little bit of its potential for work. And it isn't going to go backwards for purely probabilistic reasons. The odds against this happening it could go back for a split second. It couldn't go back from disorder to order. But over the long term, disorder will always win out. Over the long term, equilibrium will always win out. Now, let's suppose that the universe, which is stated in the standard Big Bang model, is a physical system. And it is a physical system. And let's suppose that the universe has been working over the 13.8 billion years of its existence. Suns have been burning, planets have been forming, and physicists have been thinking about it. Energy has been, physical forces have been used up. We're always moving then from a state of order to disorder. Are you with me? What if the universe had lasted for an infinite amount of time? Let's suppose it was a bouncing universe and just kept going back infinite. Or let's suppose that you had a multiverse and the multiverse had been around for an infinite amount of time. Let's suppose that you had any physical system that was operating over an infinite amount of time. Technically speaking, the universe should be a dead universe today. It shouldn't have any disequilibrium left in it. And it even shouldn't have any disequilibrium per per cubic area in it. For all intents and purposes, it should be a dead universe today. Now, there are a couple of guys who are trying to get out of this with some very, very fancy inflationary footwork. But for all intents and purposes, none of that has been verified. What we're left with is just plain old second law of thermodynamics, which makes it look like this universe or any other physical system would run out of the capacity to do work if the universe had been around for an infinite amount of time. And if the universe, therefore, has only been around, or a multiverse has only been around for a finite amount of time, what does it have? A beginning. These 2 points are actually very interesting, and Dr. Alexander Vilenkin weaves them together in a comprehensive theory. But basically, these are 2 wonderful data sets because they have such vast applicability, such universal applicability, right? The BVG theorem applies to any physical system. It doesn't matter what it is. So long as the expansion rate's greater than 0, it applies. And of course, the entropy applies to any physical system which is dependent upon disequilibrium. And of course, the use of that order in order to do work, which means, of course, that it's eventually going to reach equilibrium. It's vastly applicable. And both of these data sets from 2 different perspectives are pointing at the same thing. Not just our universe, but all known physical configurations for a multiverse, a higher dimensional space universe, a bouncing universe, they must all have a beginning. Wow, that's a very interesting thought. So interesting that Dr. Alexander Vilenkin in 2006 put it this way. It's up there on the screen. I'll just paraphrase it. It is said that a good argument will convince a reasonable person, and that a proof will convince even an unreasonable one. Well, now that the proof is in place, and the proof, of course, is a Borda-Vilenkin and Guth proof combined with the entropy evidence. Now that the proof is in place, cosmologists no longer have the possibility of a past eternal universe. There is no escape. They must confront the reality of a beginning. That's a bold statement for a physicist. They must confront the reality of a beginning. No wonder there's much ado about nothing. Let us review this for a moment. Because if there is a beginning, not just of our universe, but of a multiverse, a higher dimensional space universe, a bouncing universe, and of course a static universe is an impossibility because it's a contradiction. If there really is a beginning of physical reality, and it sure looks like that's a very good possibility, let's even call it highly probable. If there is a beginning, then prior to that beginning, prior to the beginning of physical space and time itself, physical reality was nothing. And if physical reality was nothing, then it could only do nothing. And if it could only do nothing, then it could never have moved itself from nothing to something, because it was nothing and could only do nothing. In which case, something else had to do it. And that something else has to be transcendent of our universe and physical reality itself. Not only transcendent of physical reality itself, but have the power to cause the whole of physical reality with its space and time, its laws and structures, and everything in one single blinding universal creative moment. Sounds like a creator to me. For that reason, I think many physicists, rightly so, are believers not just because of their faith. They really do think that the creation possibility is just as reasonable and responsible, if not more reasonable and responsible, than any other physical theory for the origins of physical reality itself. I'm not kidding you. Take Alexander Vilenkin at his word. But it gets even more interesting. Then you've got the component of, is this creative force outside of universal or outside of physical reality, is that creative force intelligent or not? Are you guys hanging in there okay? Sort of get it? A little bit? Good. Well, it's fascinating anyway. Okay. The main point, of course, is fine-tuning of the universe. That begins to add a whole other component to this universe. Let's just go through really quickly some of these things. Here's the main thing to remember. A fine-tuning coincidence is something which is required for any life form to exist in the universe. And generally, physicists point these fine-tuning coincidences, we talk about them in terms of the Big Bang itself. We don't want to talk about physical coincidences or fine-tuning coincidences that exist after the Big Bang, because some scientist could come along and say, well, that's explicable in terms of physical forces that we haven't yet discovered. The good point about just getting everything back to the Big Bang is there isn't any moment before the Big Bang. Everything prior to the Big Bang is causally disconnected from everything after the Big Bang. You can't appeal to a prior causation, a prior physical causation to explain the anthropic or the fine-tuning coincidence. This makes it very interesting. We're going to give some examples in a moment. Well, let's take an example right now. Low entropy at the beginning of our universe. Low entropy at the Big Bang. Remember, you need low entropy. You need lots of disequilibrium. All right, low entropy means lots of disequilibrium. High entropy, equilibrium, universe can't do anything. You need low entropy at the Big Bang for any life form to develop and for any life form to be maintained and to evolve. You can't have a life form if the universe can't do anything. You got a high entropy universe, it's all over. Sort of get it? Do you know what the odds of low entropy at the Big Bang in our universe is? Well, this physicist, Dr. Roger Penrose, went ahead and calculated it. Very fine physicist at Oxford there. And by the way, it's not a hard calculation. All you need to do is take the total number of baryons, let's say it's 10 to the 80th, and you multiply it by the entropy per baryon, right? And you basically 10 to the 43rd, and you just add your exponents, and you get 10 to the 123. And that's the total amount of entropy in our universe. And all you have to do is take the exponential of that, right, in order to get what the odds are. 10 raised to the 10 raised to the 123 to 1. That's the odds against having low entropy, absolutely necessary for any life form to develop in our universe. That's the odds against low entropy at our universe at the Big Bang. 10. It's a double exponent, everybody. Raised to the 10, raised again to the 123 to 1 against. Do you know what that number is like? That's a 10, and then in the exponent you have a 1 followed by 123 zeros in the exponent. The exponent is a trillion, 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 trillion in the exponent. If you tried to write that number out without exponential notation, where every zero was 10-point type, our solar system could not hold that number. It is the same probability of a monkey typing the entire corpus of Shakespeare by random tapping of the keys in a single try. This is highly improbable. I mean, basically, you come to the monkey and you go, I want the corpus of Shakespeare. The monkey, eek, eek, happily, he begins randomly tapping on the keys, right? You come back a few weeks later, and there's Macbeth in perfect folio condition. And you begin to think, wow, that's highly improbable. And then there's Richard III. Again, it's done perfectly. And you begin to suspect perhaps someone who, with a very good knowledge of Shakespeare, as well as good typing ability, has helped the monkey in my absence. That's the odds of having low entropy at the Big Bang necessary for any life form to develop. This is really hard to explain. Right? That much order in the universe is hard to explain. I'll give you just a few other examples and you'll get the point. Back to the Big Bang. We have 20 constants in our universe. A constant is a number. It's a number that remains constant throughout time. So it was the same in the past, going to be same in the future. 13.8 billion years ago was this way. It's going to be 13.8 billion years from now. It's going to maintain the same value. It's everywhere the same in the universe, irrespective of space and time. The constant remains the same. What does the constant do? The constant is a number that allows for the interaction between forces or the interaction between space-time and for those universal forces. So essentially, constants are minimums, constants are maximums, constants are ratios, constants are absolute numbers, etc. So let's just take some examples of the 20 constants. The speed of light constant, right? I think everybody knows the speed of light is constant throughout the universe, 186,200 miles per second, 300,000 kilometers per second, right? That's a constant. We have 4 forces in our universe, right? We have electromagnetic force, we have the gravitational force, the strong nuclear force, and the weak force. And each of those forces has constants attached to it. So the gravitational force has the gravitational constant, right? And that's a very defined constant. It's a very defined number. The weak force has the weak force constant. The strong nuclear force has the strong nuclear force coupling constant. And the electromagnetic force has 3 constants attached to it. The mass of the proton, the mass of the electron, and the electromagnetic charge. And then you have Hubble's constant, the cosmological constant. There's 20 of those babies. Now here's the deal, everyone. If you alter those constants by just a little fraction, higher or lower at the Big Bang, then life is impossible. It could have been any. Those constants, those 20 constants, could have easily been higher by a huge margin and could have easily been lower by a huge margin because there is nothing special about those constants except the convergence of those constants is necessary for life. But it doesn't make any one of them more probable than the next. And that's really weird. Let's take some examples. If you altered the weak force constant or the gravitational constant by only 1 part in 10 to the 50th. You with me? 1 part in 10, that's like a decimal point, 49 zeros and a 1. It's a really teeny fraction. If you altered it by 1 part in 10 to the 50th, higher or lower than the value it just happened to have had at the Big Bang, then either the universe would have continuously exploded in its expansion. Cataclysmic explosions throughout the 13.8 billion years, which, by the way, is very bad for life forms. Incinerates everything. Or the universe would have collapsed back into itself in essentially a Schwarzschild black hole, with the matter density becoming almost infinite, which means infinite squishing power, which is really bad for life forms. When the entire mass energy of the universe is collapsed into 10 to the minus 33 centimeters, life doesn't stand a prayer. You mean we avoided complete cosmological disaster by a fraction of 1 part in 10 to the 50th in these two constants at the Big Bang? Do you know the odds against those constants having those precise values within that narrow margin of error at the Big Bang by pure chance? Monkeys typing Shakespeare again. Same odds. One monkey typing the corpus of Shakespeare by pure chance. Oh, by the way, if you altered the strong nuclear force coupling constant, you just made that 2% higher, the entire universe would be hydrogen. There would be no element heavier than hydrogen possible. And if you made it 2% lower, there would be no hydrogen. Now, if there's no hydrogen, I can assure you of this: no water, no nuclear fuel, no fusion, very bad for life forms. Alternatively, if you have no element heavier than hydrogen, like carbon, nitrogen, iron, very bad for life form. Go ahead. I defy anyone to make a life form out of purely hydrogen atoms. People do it. Completely impossible. You mean we averted complete cosmological? You got it. By a factor of 2% in the strong nuclear? Yeah. Take 4 of the constants here. The gravitational constant, the mass of the proton, the mass of the electron, or the electromagnetic charge. Alter any one of those babies by 1 part in 10 to the 39. You with me? 1 part in 10, that's a decimal point 38 zeros in a 1. Higher or lower. And by the way, they could have had much higher values. They could have had much lower values. But they got it right in the right zone. But if you altered them by 1 part in 10 to the 39th, then either every star in our universe would have been a blue giant, which would have incinerated everything, or every star in our universe would have been a red dwarf, in which case everything would have frozen. Both alternatives, exceedingly bad for life forms. You mean we averted complete cosmological disaster in all of the stars of our universe? Right? I mean, our star, we're so lucky. I mean, here we are. I mean, we've got these 4 constants, and they're so precisely valued. I mean, we're sitting right on the cusp of thermodynamic, instability, right? I mean, and we're just sitting there, and yet there are tons of stars like ours, all because those constants just came out the right way at the Big Bang. Case. So what are we up against? I mean, if we got monkeys typing Shakespeare again and again and again for the mass of the proton, mass of the electron, electromagnetic charge, strong nuclear force coupling constant, weak force constant, low entropy at the beginning of the universe. I mean, we got so many monkeys producing Shakespeare by pure chance so many times. I mean, the odds of this happening, there's only 2 alternatives. I'm just going to tell you right now. This did not happen in our universe by one-off, pure chance, random selection. Not even Stephen Hawking buys that one. Well, what are the 2 options? A multiverse or a really smart creator? That's the only options you have. The multiverse, of course, is going to be something selected by people who don't want to believe in a smart creator, setting the values of the constants. So what does the multiverse afford? Remember, it's possible. It's hypothetical, but it's possible. You could have a multiverse burping out all kinds of bubble universes. And maybe you not only have 10 to the 123 bubble universes. We know that every multiverse has to have a beginning, right? But maybe it goes back so far back in time that you not only had 10 to the 123 universes, you had 10 to the 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 123 bubble universes. So finally, you could have one universe like ours. As Paul Davies once put it, that formula for the multiverse, well, that's like bringing excess baggage to cosmic extremes. What he meant to say was, it's a violation of the law of parsimony, what's called Occam's razor. But that doesn't prove that it's false. It just proves that the multiverse hypothesis at that level of extreme is contrary to what nature normally is. Nature's elegant. Nature is parsimonious. Nature doesn't have just needlessly duplicated systems, right, in order to produce ordered effects. But that doesn't disprove it. The multiverse could still be the case and could still explain our universe with all of its constants able to produce a life form like ours. The real kicker, though, is this. Every known multiverse hypothesis today requires fine-tuning in its initial parameters and constants. Uh-oh. You can't have a random multiverse, ladies and gentlemen. You can't have a multiverse that is literally spewing out bubble universes sporadically and at random. You can't do that. Why is that? Because universes within a multiverse have an extremely strong gravitational effect. Huge. So if these universes start coming, right, that the gravitational force of these universes within the multiverse, they start coming even within remote proximity of one another, right? The gravitational forces start just, shaking these universes like a jello, which is exceedingly bad for life forms. No, what you're going to need is a real slow, orderly roll of bubble universes that can never create interference one with another. And by the way, whatever you do, you don't want bubble universes colliding with each other. Whew, boy, is that bad for life forms. So you need a slow roll of the bubble universes. But if you're going to get a slow roll of the bubble universes, you're going to have fine-tuning in the initial parameters and constants of the multiverse. Therefore, the multiverse cannot be a perfect solution to the problem of design, to the problem of order. All you're doing with the multiverse is moving the problem back one step. Now it's not where did the order of the universe come from so that we can have life on Earth. Now it's where did the order of the multiverse come from in its initial parameters and constants so it could give rise to bubble universes which wouldn't collide into each other so that we could have a bubble universe like ours on Earth. You guys with me? For this reason, Sir Fred Hoyle kind of put it this way. So, oh, by the way, Sir Fred Hoyle was one of physics' most atheistic physicists. But one day, his partner, William Fowler, came into him and said, Fred, do you know what the odds of beryllium, oxygen, helium, and carbon having the precise resonance levels that they have in order to have an abundance of carbon in the universe? Fred said, no, I think I do. He says, here are the equations. And Fred goes into his office, and here's the quote. I'll paraphrase it. I don't think there are any blind forces worth speaking about. It seems to me that some super-calculating, super-intellect has monkeyed with the constants of physics and those of chemistry and biology as well. I consider this conclusion to be beyond the shadow of a doubt. He later went on to say, the odds of having an abundance of carbon in our universe, given the resonance levels, is tantamount to, well, a tornado going through a junkyard and assembling a Boeing 747 ready for flight. What's the point? If you take those three foci on that, on that triangle, when you start looking at the Borde-Vilenkin and Guth proof, and its vast applicability to multiverses, higher dimensional space universes, etc. When you start looking at the vast applicability of entropy, and the fact that the entropy evidence and the space-time geometry proof evidence both point to a beginning of physical reality, not just a beginning of our universe, but a beginning of physical reality. And if you look at those fine-tuning coincidences, those strong anthropic coincidences, which, by the way, are not adequately explained by a multiverse theory, because a multiverse theory has to have fine-tuning in its initial parameters and constants. When you assemble those three things together, I think we can say with many physicists that it's just as reasonable, if not more reasonable, to believe in an intelligent creator than it is to believe in a multiverse, which would have to have a beginning anyway and would have to have fine-tuning in its initial parameters and constants. Perhaps the best explanation lies in the actual universe. Perhaps the best explanation lies in the creator itself, an intelligent creator itself. Now, of course, we know that Dawkins and other people have tried to forward arguments to try and show that a creator would have to be far more improbable than anything that it creates. That is simply a false argument, and it can be easily disproved. And if we don't get to it in the Q&A session tonight, where would you go? MagisCenter.com, first landing page, Science, Reason, and Faith, and you would be able to get it. I'm going to end right now just with a quote from Robert Jastrow, the founding director of NASA's Goddard Institute for Space Studies. And he wrote a book a while back with a quote that applies just as much today as when he wrote it. It was a book called God and the Astronomers. And this is what he said, and again, I'll paraphrase it. Scientists unshackled themselves from the domain of superstition, took on a methodology which was mathematical, empirical, and hypothetical deductive, and carefully began to climb the structures, this mountain of knowledge. They came to the top, pulled themselves over the final precipice, and found a band of theologians there, awaiting them for centuries. Thank you very, very much. Thank you very much. We do want to get to the Q&A, but I know that people may want to take a restroom break. But could I ask people if you want to just go to the restroom, and would you mind if we launch just right into the Q&A right now? Okay, that'd be splendid. Somebody will help me with the Q&A since I have a little bit of a
We're going to ask them to come in and use the
splendid.
right here. They can just line up.
Splendid.
Father Richard Spitzer, Robert Spitzer, I was just wondering, is it true that in Einstein's general theory of relativity that gravity can bend time?
That gravity bends time?
Yeah.
Yes. As a matter of fact, it is. Let me just give you a quick rundown. It's a very good and intelligent question. In the general theory of relativity, what Einstein did was, he put together this effect of the speed of light. The effect is called the effect of special theory of relativity. It's called length contraction and duration dilation. Because of the constant speed of light, if you put a ruler in a rocket ship, let's say, and you start accelerating it closer and closer to the speed of light, you can actually prove that the ruler must shrink. It will start getting smaller and smaller and smaller the closer you get to the speed of light. But the opposite will happen, namely with respect to time. with our clock. So if we have a clock with a swinging pendulum, right, or at least going in the direction of the rocket ship, then what's going to happen is that the pendulum is going to slow down. So that's going to call the expansion of duration. So you have to have what's called the Lorentz-Einstein transformation in order to figure out what the size of a ruler is in a rocket ship compared to the rulers that I have on, in my reference frame, and the pace of the clocks, right, in terms of, my reference frame, my clock and my reference frame. Now, this has been proven over and over again. Huffaly and Wilson's atomic clock expansion, the Mosbauer effect, right, the pi meson, mu meson decay experiments, etc. Right? This has been proven again and again and again. Yes, inside a highly accelerating rocket ship, time is going slower, and the measurement of time is going slower. And yes, in fact, the ruler is shrinking. Now, what Einstein did in the general theory of relativity is he linked all of this up to gravity, showing that special relativistic effects were also, not only predictable, but were also traceable back to the curvature of space-time. So therefore, could the curvature of space-time actually, for example, in a black hole, the curvature of space-time, right, because of the density of mass energy, when the density of mass energy is very, very high, right, and it's going to collapse the geometry of space-time in the area in which it exists. But remember, all space-time is linked to all other space-time. So even though you get, you have very, very, very small units down near the base of the black hole, about 10 to the minus 33 centimeters, as you kind of go out, it gets a little bigger and bigger and bigger and bigger. Now, remember, it's not just space that contracts, it's duration that dilates. So basically then, if you have some kind of an orbital that's coming in, right, to this black hole, and it gets caught in the black hole and it's getting swept into the curvature of space-time, which is smaller and smaller and smaller and smaller as it's getting toward the base of the black hole, it's actually, right, the matter is actually taking on the space-time geometry of the continuum in which it's traveling. So it's going to get smaller, right? And so that's why you'd have like a star gets sucked into a black hole. It's going to turn into a spaghetti, right? Because the outside's going to be stringing out there a little bit, while the inside is getting denser and denser and smaller. But not just that, but the actual measurement of time. So if a rocket ship was coming in there with a clock, what would be happening to that clock as you got toward the base of the black hole? It'd be slowing down. Almost nothing there at all. It's not, but of course, as it's going down, the pace of the clock will be faster behind and it would be slower toward the front. And it would be bending time and bending space. Exactly. Because, of course, space-time is not distinct from mass energy. Mass, energy, and space-time are a single organic whole. And of course, inasmuch as they are, we not only have this weird coincidence of things, but actually the universe is capable of sustaining life itself. Thank God for the bending of space and time. If we didn't have it, we wouldn't be around. Great question.
Thank you.
Next.
I grew up with the idea that the universe was physically infinite. You made a statement earlier tonight, I believe, about believing the radius to be like
about 100 billion
light years, which suggests that if theoretically we could travel to the end of the universe, after 100 billion light years it would end. Would we hit a wall? What would be there at that point?
No, you just keep going, as it were, around the circumference of the universe. The topographies range. There are many, many theories about what the universe looks like, geodesically and geometrically. But eventually what would happen is, no, you wouldn't be hitting a wall. You would just be repeating yourself. It was the old Einsteinian thing. What's the furthest point you can see looking through your telescope if you went back 13.8 billion years in time? If you were around 13.8 billion years ago, you'd see the back of your head. Yeah. So the light would have come, as it were, full circle. Now, of course, we don't think the universe is a perfect sphere today. We think there's all kinds of other possible configurations. But nevertheless, unfortunately, no walls to hit, just reroutes to experience. Good question, though. Yeah, but it looks like it probably is finite. There are some ways in which you could say that the universe will continue to expand we call that a potential infinity. But right now, we don't think that the universe is an actual infinity. We really do think it's probably about 100 billion light years in radius, somewhere in that neighborhood. Good question.
Hello, Father. Simplistically,
Yeah.
what do you say to people who do not believe in evolution, or say you're not a Christian if you believe in evolution?
Besides laugh? No, I'm just kidding. No, no, I'm just kidding. Well, I think this. I bring out, Joan, can you actually flip over to John Paul II's message to the Pontifical Academy of Sciences? It's one of the evolutionary, just flip down to evolution. Here's a nice little message from John Paul II. By the way, the Catholic Church has long held that the physical evidence, the chemical evidence, the fossil evidence, and the genetic evidence point very, very profoundly to a good possibility of evolution. It goes all the way back, really, to Pope Pius XII. And Pope Pius XII in 1951, I believe it was, wrote an encyclical called Humani Generis. And what he indicated was that the theory of evolution, that Catholics could believe in the theory of evolution so long as they did not compromise on one thing. They couldn't compromise on God creating a unique individual transmaterial soul. So you couldn't reduce a human being to mere organic or physical constituents. You'd have to believe in a soul. So the idea would be then, by the way, it's not hard to believe in a soul. Have you seen the three most recent studies of near-death experiences? The one that was published in The Lancet by Pim van Lommel, the one that was published by Sam Parnia from the University of Southampton, right? I mean, where you're dealing with thousands of cases that were monitored and so forth and so on. Hey, if you don't believe in the survival of human consciousness after bodily death, then tell me one thing. Why do 80% of blind people see for the first time when they're clinically dead more than a minute after they've had a heart attack without any oxygen in their brain? They couldn't see in their material bodies to begin with. How can they see for the first time when they're clinically dead? You explain that to me, and then I can tell you why I believe, definitively that human beings have a transphysical soul that will survive bodily death. But that's a whole other story. That was the only condition that Pope Pius XII established for, belief in evolution. Then John Paul II comes along, and John Paul II, because he studied the fossil, genetic, and chemical evidence, basically he comes and says, it's more than a hypothesis. It really is closer, we're getting closer and closer to a validated theory. And the evidence really is there for that, and there's no dispute with the Bible, and I'm going to talk about that in 1 second. Can people, though, can somebody read that for the audience? My eyes are not good enough to read it, but it's just a quick summary of what he says.
Quotes, right?
2 quotes, yeah.
Taking into account the scientific research of the era and also the proper requirements of theology, the encyclical Humani Generis treated the doctrine of evolutionism as a serious hypothesis, worthy of investigation and serious study, alongside the opposite hypothesis. Today, some new findings lead us toward the recognition of evolution as more than a hypothesis. The convergence in the results of new multidisciplinary studies constitutes in itself a significant argument in favor of the theory.
In favor of the theory. So that's our own Pope John Paul II. I think Catholics are very free to believe in it. I think the evidence points to it. The problem, of course, is the seeming contradiction between the Bible and the theory of evolution. It was the same Pope, Pope Pius XII, that actually wrote another encyclical back in, I believe it was 1942, and it was called Divino Afflante Spiritu, and we have a little slide on that. This is a good little encyclical to sort of take note of, because at that point, Pope Pius XII declared that Catholics essentially hold, you know what the theory of inspiration is. You know, how does God inspire the biblical author? There's a so-called dictation theory, and there's also the so-called collaborative theory. What Pope Pius XII has said is that Catholics hold to the collaborative theory of inspiration. That means that when God speaks to the biblical author, God does not go to somebody in 500 BC and go, biblical author, I'm going to dictate something to you. Just take this down. This is how it went. In the beginning, there was a cosmic space-time geometry configuration that burst into existence along with quantum dynamics, where the four forces were unified in a single microcosm. After 10 to the minus 24 seconds, the first force, the gravitational force, rolled off and became a space-time continuum. And then the strong nuclear force rolled off 10 to the minus 16th of a second later. And that left the electroweak force, which finally separated. And then once the electroweak force separated, the electromagnetic forces burst into a fine energy which moved through a Higgsian field. And when it did so, acquired rest mass. And the rest mass immediately gave rise to a pool of quarks, which later became protons and neutrons, eventually emerging in stellar nucleosynthesis and all of the galaxies of the universe. That poor biblical author, he wouldn't have understood a thing that God was saying. It wouldn't have worked. So what did Pius XII say? He said, that's not the picture. What is the point of the Bible, and what is the point of God inspiring the biblical author? To give truths of salvation, to give sacred truths necessary for salvation. How much of what I just said of the contemporary physical account of creation, how much of that is necessary for your salvation? You got it. 0. What is necessary for your salvation is what the biblical author said in the categories and the structures and the concepts of his culture and in his time. The biblical author is wrestling with all of these other competitive myths, right? These so-called epics of creation, like the Gilgamesh epic. And of course, they've got many gods. So what does the biblical author come back with? One God. And then, of course, they got the nature is godlike. So you got the sea god and the sun god and the earth god and all kinds of. The biblical author goes, no way. It's just one God, and everything else is a creation. Now, how right he is, of course, according to the physics of our day. But of course, necessary for salvation is none of these natural things are gods. They're just creations of God. There's but one God. I mean, I think it's so remarkably stunning that he knows. The third thing that he says, and of course, contrary to the Gilgamesh epic, is that human beings are literally created and made in the image and likeness of God. They have divine value. You have divine value. You are not cannon fodder and playthings for the gods, as in the Gilgamesh epic, right? So the key thing, right, is he's giving these truths of salvation, which are still truths of salvation for us today. But to try, said Pope Pius XII, to make the poor biblical author into a scientist is ridiculous. It has nothing to do with salvation. It doesn't correspond, to the capacities and the culture of the biblical author. They need to hear the words of salvation back then as much as we need to hear it today in this scientific age, right? Remember the old thought of St. Thomas Aquinas? Quid recipitur est recipitur in modo recipientur. Whatever is received in the manner of the receiver. You can't give physics to a guy who's never heard of calculus. Won't work. So the idea of a dictation theory or a literalist theory of inspiration is not, we just don't hold it as Catholics. We do have very good evangelical brethren, some of whom hold to a young earth view and hold to this view. That's fine. I mean, they believe in the essential thing, God, the creation, the soul. I can discourse with those guys. I don't think I have to force them into it, but for all intents and purposes, I have got very good reasons to believe in evolution scientifically, which my church does not refute, and it doesn't have to be refuted because, of course, the Bible is not there giving scientific truth. Science gives physical descriptions and explanations of the universe as we know it. Theology and biblical exegesis is meant to do one thing: give sacred truths necessary for salvation. Let science be science and let theology be theology, and we'll all just be happy. And that's, I think, the short answer to your good question. Thank you. I think we ran, or should we have one more?
One more.
Okay, one more, excuse me.
We understand since the beginning of recorded human history, we accept the physical laws as we understand them to be universal, that they're unchanging throughout our universe. We also know from many recent discoveries that there are literally thousands of planets in our universe that are in the temperate zone that will support life.
That's true.
So we can say with a high degree of probability that life exists elsewhere in our universe.
That's true.
Whether that life is human life or if it is intelligent life,
That's true.
We don't know. Is there are there any theories regarding the existence of intelligent life elsewhere in the universe that is endowed with a soul in the sense that humans are? And if that is the case, then is a question, is heaven a universal community?
Good question. Hey, Joan, can you just go to those slides about the exoplanets and the number of, pardon? Yeah, on aliens, yeah. Yes, exactly what you have said is correct. There are literally probably somewhere in the neighborhood of 10 to the 11th exoplanets in the habitable zone out there, which could have certainly amino acids and certainly could have lipids necessary for cell walls and cell membranes, and certainly could also have some kind of nucleotides and ribosomic structure. So it's possible. So as you correctly said, it's pretty clear that there's probably some other life forms out there, for sure. But the key question are there intelligent life forms out there? And the answer is simply this: if God wants them to be, there are. And the reason you have to say it that way is because intelligent life forms like ours are not explicable in terms of physical and biological laws alone. There are 5 huge problems with moving from us, from a physical universe to us as transcendental beings. By the way, I have a brand new book coming out called The Soul's Upward Yearning, Clues to Our Transcendent Nature from Experience and Reason. If you're interested in this problem, take a look at it. But here are the 5 big things. Number 1, those near-death experiences I just mentioned, the evidence now is really getting so good. And contemporary neurologists and neuroscientists are already saying, no known physical theory can explain these things. No known physical theory is able to explain accurate veridical perception, after clinical death, sometimes for up to over a half an hour. I mean, how blind people, 80% of blind people can see after clinical death, etc. So that's a problem. How we have some kind of a soul, some kind of consciousness that is detachable from our physical bodies. If that other life form is like us, then that other life form has has consciousness that's detachable from its physical body. But how could it have that? Because then the universe couldn't explain its consciousness, because its consciousness didn't emerge from its brain. Its consciousness is detachable from its brain and can exist after the death of its physical brain. God has to do it. Biology, physics, science can't do it. Number 2, there's this little theorem called Gödel's theorem. Gödel was a German mathematician who had a very interesting proof, Gödel's proof. And by the way, if you want to know all about Gödel's proof, where would you go to find out about it? MagisCenter.com, precisely. But what he showed was that human beings mathematically are trans-algorithmic. That is to say, we do not need any kind of rules or algorithms in order for us to function mathematically to invent a new theorem. We are already beyond any known theorem. We can leap ahead without making recourse to past algorithms. And of course, past algorithms will never explain new mathematical theorems. We are trans-algorithmic mathematical thinkers. And if you're going to explain that, you're going to have to get beyond algorithms. And if you get beyond algorithms, you're going to have to get beyond not just physical processes, like classical physical processes, you're going to have to get beyond quantum physical processes. This is a fascinating thing, you little ultimatizers, you are capable of. Number 3. This came out from Plato 2,400 years ago. Human beings have a desire and an awareness of perfect truth, perfect love, perfect goodness, perfect beauty, and perfect home. That's what we want. We don't want just any love. We want perfect love. We don't want just any justice or goodness. We want perfect fairness and good. We don't want we want perfect truth. We don't want imperfect truth, right? We rack our brains to solve every kind of question. My little nieces, right? They want the complete set of correct answers to the complete set of questions. Uncle Bobby, why is this? Because of that. Well, why is that? Because of this other thing. And why is that? And finally, you got to tell them time out because you're in the deepest modes of quantum theory. I mean, it's just, honestly, we are ultimate, we are transcendent beings. We're seeking the transcendent. We're seeking the perfect in truth, goodness, justice, beauty, and home. You can't explain that with physical theories. Number 4, I won't get into the whole thing. There's a thing called The Hard Problem of Consciousness by David Chalmers. Read my book, The Soul's Upward Yearning. The point I'm trying to get to is these 5 things make you qualitatively different from any classical physical and quantum physical process. Looks like you got a soul. And if any alien life form is like us, they're thinking about God, they're thinking about perfect love, they're doing Gödelian trans-algorithmic mathematics, they're capable of surviving bodily death, their consciousness, and you spot one of those babies, I would say, first thing, assume God created them with a soul. Second thing, catechize them. Third, baptize them because they're ready. They're literally like us, transcendent beings. Really, really great question. Thanks, everyone.
Thank you, Father Robert. We are very honored to have you. It's a very beautiful day to have you here today. We're going to have a little reception afterwards. There's books available for you. Thank you, Father. Grazie. Grazie. Beautiful.